developing the models for plasticity or elasticity, or what you can do with such models. So we have been discussing those things in the last class, but today is we are slightly deviating from the flow of the course, and we are addressing the microstructural behavior in a very brief, very simple way. Okay, and even the very primitive way as well. uh, the reason for including today's class is that without understanding at least the basics of uh, that microstructural behavior, um, uh, it would not be possible for us to to when we actually look at those models, how where does those models come from of plasticity. Okay, to anticipate that would be very hard, and it is also not a complete view of plasticity without the microstructure or the metallurgical or having the material science background in that. Okay, so having said that, can you see my screen?
Yes, sir.
আচ্ছা, ঠিক আছে। তো uh, আজকে যেটা আমরা ডিসকাস করব, okay, I'm sure you are familiar with that part of the study. It's only from a UG course, and to be frank, the images that I'll be showing, I'm getting those from the book by William D. Callister. Okay, uh, so if you have that book, you can directly go through that. Actually, it is going to be helpful for today's course if you go through the chapters going from chapter number 3 to chapter number 7. Okay, I got these images from there. Okay, so so let's start with the presentation. One second.
স্যার চ্যাপ্টার নাম্বার 3 আর চ্যাপ্টার নাম্বার 7 এই দুটো চ্যাপ্টার, মানে চ্যাপ্টার নাম্বার 3
No,
থেকে
from
চ্যাপ্টার
chapter
নাম্বার
number
7?
3 to chapter number 7.
আচ্ছা, 3 টু চ্যাপ্টার, ঠিক আছে।
Okay, so let's start the discussion on microstructure. And as you know that no microstructure is perfect, no crystal structure is perfect, otherwise we would all be having single crystal materials with directional properties. Okay, but we know naturally most of the materials that we work with, okay, day-to-day life, they are all, if not homogeneous, they are at least isotropic. Okay, now the two terms homogeneous and isotropic have different meaning. Homogeneous means if you move from one position to other in the material, okay, the property is not changing, and that property could be Young's modulus or density, whatever. But let's take a property such as Young's modulus. Okay, that's where the direction comes in. Now instead of changing the position along a line, if you change the orientation, that means instead of applying a force in x direction, if you apply a force in the y direction, okay, do you get the same amount of deformation as in the previous case? If you do, then you'll have to assume that the Young's modulus in x direction and y direction are the same. Now, as I mentioned, in a day-to-day life, and that property would be isotropy. If that is not the case, then it is an isotropy. Now, this isotropy and anisotropy again is a macroscopic term used for describing the material behavior. What happens inside is that the material has, if the material is a single crystal or a single grain entirely, if the entire geometry is the single grain, okay, which means the atoms are stacked in a given orientation. Okay, and there are a lot of orientations. You would see some of them in this presentation as well. So if they are oriented, if all the atoms in a component are oriented in a given fashion, okay, then the material starts showing directional property. Then the Young's modulus in x and y direction may not be same. And if the x and y is same, maybe somewhere between x and y may not be same. Okay, so so on the other hand, if the material is multi-grained, if it is composed of different grains oriented in different direction, I mean, the grains are formed by change in orientation, as simple as that. So having grains means you have atoms oriented in crystals along different direction, and therefore you do not get the directional effect, and that's when the material becomes isotropic. Now, now that is that so you need to understand that isotropy is not uh, coming from a perfect crystal. It is coming from multigrain materials, whereas the anisotropy is coming from anisotropy would be coming from a more oriented, I mean more organized set of uh, grains. Okay, now here we do not start with grain, but we start with the simplest form of defect that we can find in a material. Okay, now if there are no impurity materials, that means if there is no sort of solid solution. Okay, I hope you understand what is meant by that. I mean, like if the iron is the base, okay, there can be different alloying elements that you can put on iron. For example, to make stainless steel, you put chromium and nickel, okay, mostly, and then there are other components, and of course a very tiny bit of carbon as well. But I'm talking about other metal alloying elements. Okay, so if that is not the case, then also you can have some defects. Okay, so there can be in a pure material, that means if there is no single atom from a different material in a given, so that's the picture in the left. There you can have two types of impurity. One is a vacancy, that means an atom is missing where it should have been. Okay, uh, and does that have any effect in this crystal structure? It does. Okay, and the crystal structure would not be looking this perfect. And when we look at the the next few slides, we will know how the structure would look like. And the other thing could be that that same missing atom might find its way somewhere else, and maybe it just lost its home, and it is taking a shelter between a few other atoms, and thereby pushing them. Okay, which is the the furthest circle in the left. Okay, showing the self interstitial. Okay, so again the crystal structure would not remain the same. Presence of an atom which is pushing the other atoms away would distort the crystal structure, and similarly presence of vacancy would also distort the the crystal structure, and the crystal structure would have a tendency of collapsing into the vacancy. Okay, so as you can imagine, in place of self-interstitial defect, there would be a compressive stress field in presence of the the vacancy. There would be a tensile stress field. Now, if you look at the picture in the right, there we have the impurity atoms. Now, if the atom is really tiny, it can take shelter between the atoms, not in a not in a vacant position, okay, but in a interstitial position. Okay, I mean it's not occupying one of the positions in a given crystal. Okay, and what are the different types of crystals? We'll look them in a minute. But let's take this simple example of the crystal that is shown here, which is like hard sphere model, all touching themselves. Okay, so it is not occupying any vacant position in that. Okay, whereas if you look at the green sphere right there, it is occupying the position of one of the blue spheres right there. So it is substituting for that blue atom. Okay, so imagine that is an atom of chromium occupying the position um, in the iron solvent. Okay, so let's say therefore whatever element is smaller in quantity, we would call them as the solute, and the solvent is the major material. So iron, you can imagine in any iron alloy, you can imagine that in ferrous alloy, iron is the solvent, and let's say that green colored atom is from chromium. Okay, so it is taking the position of one of the iron atoms, so it is called a substitutional atom. Okay, and and let's say that tiny orange colored sphere is from carbon, and that is occupying a position between a set of iron atoms. Okay, it's not occupying one of the positions of the iron atoms. Okay, because it's so tiny. Now, obviously, whenever there is an interstitial atom, however tiny, there would be a compressive field. But what happens with the chromium atom? Do you have any sort of compressive or tensile field right there? That is a question. Do you think there should be any compressive or tensile
No,
field?
sir.
Huh?
No, sir.
No,
No.
sir. Okay, okay. But why are you imagining that the size, okay, of the chromium atom is supposed to be same as that of iron atom? Obviously, they have different atomic numbers. Okay, and you do not know how many um, orbits should be there. Okay, or for electrons, you do not know how many of them would be there. So chromium could be a larger atom or even a smaller atom than iron. Okay, if it is smaller, okay, it would have the similar effect as vacancy. If it is larger, it would have the similar effect as the self-interstitial. Okay, in a smaller scale, but similar effect. Okay, so they do produce compressive and tensile field depending on the size of the impurity atom. Okay, so these are the major four types of point defects. Okay, and when the point defects line up like one after the other, okay, let's say a set of vacancies line up, okay, not in a straight line, necessarily not necessarily in a straight line, maybe in a curved line. Okay, but when they do line up, they form line defects. Okay, so here we are showing two major types of line defects. One in the middle uh, is called an edge dislocation. Okay, and one quantity that is important over here is called the Barger vector, that is symbolized with B and shown with an arrow, which in this case is actually perpendicular to the direction of the line defect. Now, what is the direction of the line defect? If you look at this, the central picture right there, the direction of the line defect is perpendicular to your screen. Okay, because you see a set of missing atoms. Okay, in this example, a set of missing atoms. It need not be a set of missing atoms. Okay, it can be any other type of point defect, but the set of point defects are aligning, okay, perpendicular to the plane of the stream, and that's how the line defect has formed. And the Barger vector essentially showing that uh, that the that you know uh, so as you so okay, okay, one more thing before going into the details of the Barger vector. So that's sort of an edge dislocation, that's sort of an line defect. So line defects are termed as dislocation, and that sort of a line defect is called an edge dislocation. Okay, so the impurities, sorry, the point defects have aligned themselves in a mm, align themselves. Now, how do I know this is an edge dislocation? In an edge dislocation, the Barger vector is perpendicular to the direction of the line. Now, what is a Barger vector? If you look at the um, top side of the the, let's say this is a grain. So top side, if you look at the top side of the grain, okay, so you see that there are around seven atoms that are aligned on a given line. Now, obviously, uh, there is a so-called half plane of atom. Okay. Now, if you imagine this entire crystal structure is okay, so the edge dislocation is denoted by that red perpendicular line. Okay, so red perpendicular symbol right there. So on top of that, and if you go infinitely at the bottom of that, okay, so you would be seeing that obviously around that dislocation there is a transition that is going on. But if you are much further below that than that, or much higher above than that, then there is crystal structure is perfect. Okay, if there is no other dislocation, then the crystal structure would be perfect. Okay, and the top half of the plane of atoms is called the the semi-infinite plane. Okay, you can regard it as a semi-infinite plane or half plane of atoms. Okay, so in the top half, okay, and in the bottom half, if you look at this, the essentially the change in the the span of all the atoms has changed by a single unit, and that unit is B vector, the Barger vector. Okay, so So as the the atoms align from top to bottom, okay, they have to compensate for, they have come closer to, so the atoms in the left and the right, they have come closer by how much amount? That amount is your Barger vector. Okay, and that Barger vector is essentially perpendicular to your edge dislocation. Okay, and at this point I want to mention that plastic deformations in the material happen because the dislocations move, and dislocations move. So why we are emphasizing on Barger vector? Of course, when undergrads, when you studied material science, you had no idea about the importance of Barger vector. But the thing is that Barger mm, uh, what is the significance of Barger vector? That mm, that the direction of the Barger vector is the direction in which the dislocations move, and as the dislocations move, okay, the plastic deformations happen. The macroscopic behavior, that is the plastic deformation, the plastic strain, that is a result of the shift of the dislocations. Okay, and the dislocations move in the direction of their Barger vectors. Okay, so in a way, you can think the Barger vector is a quanta of dislocation movement, or a Barger vector is a quanta of plastic deformation. Okay, so in quantum mechanics, you might have come across different the quantum particle, such as your photon, okay, or thermion. Okay, so photon is the tiniest quanta of light, okay, or any amount of electromagnetic wave. Okay, same goes for thermion, for heat transfer. So similarly, you can think of that anytime a dislocation has to move, it can only move by the tiniest distance called the Barger vector. Okay, the step cannot be any smaller than the Barger vector. And as these Barger vectors add up, you have a macroscopic plastic strain that is measurable with the macroscopic instrument that we use to measure strain, such as an extensometer. Okay, so that is with the edge dislocation. The picture in the right is called a screw dislocation. Okay, and you see a sort of tearing effect happening across the crystal, and that essentially is creating as has has is creating essentially that dislocation that we are talking about. Now, what is the dislocation? Now, with the edge dislocation, it is very clear which line is the dislocation line. It is a line, at that perpendicular symbol that is perpendicular to the plane. Okay, that essentially is the edge of the half plane that is on the top. Okay, so with edge dislocation, that's why it is called an edge dislocation. With edge dislocation, it is extremely clear. Okay, but with screw dislocation, the direction of the screw dislocation is the axis of the screw. Now, what is screw over here? If you look at that distorted region, if you look at the atoms at the top and the atoms at the bottom, okay, come to the picture below. Okay, not the 3D picture, the isometric view, come to the 2D picture of the screw dislocation. So that is below, that is, the picture B. So you can imagine that there is certain spiral sort of behavior is going on. The atoms at the top, okay, uh, if you go by them, then once you reach uh, the end, you can look at the bottom plane. Okay, and in the bottom plane, it is following another line. So it is, so on a given plane it is zigzag, but if you combine the two planes, it is actually kind of rotating about an axis, and that axis is this line AB over here. Okay, that line AB that you see, it is actually, if you look at the top plane and the bottom plane, it is actually essentially rotating about that axis, and because of that, it is termed as a screw dislocation, and AB is essentially the dislocation line here. Okay, so line defect that we are talking about, that line itself is AB. Okay, um, again, B is the Barger vector here, and as you now, if you can imagine, as you try to tear the crystal even further, okay, in which direction the dislocation would move? It would move, the dislocation would move along its axis. Okay, that means the Barger vector is parallel to the axis. So unlike the edge dislocation, in the screw dislocation, the Barger vector, that is a quanta of dislocation movement, that is parallel to your axis. Okay, and in the extreme right we have this the third figure, which shows how there can be change from a given screw dislocation to an edge dislocation. The screw dislocation is represented by a the rotation symbol. Okay, so in between the screw and the edge dislocation, you have a mixed behavior. So how do you identify a given dislocation is edge or screw? By its Barger vector. If the Barger vector is aligned with the dislocation, it is a screw dislocation. If it is normal, it is a edge dislocation. And if the dot product itself is non-zero but not maximum, okay, so that's how we determine whether it is perpendicular or not. If the dot product is zero, the Barger vector and the direction of the dislocation, then it is an edge dislocation. If the dot product is the maximum, okay, then you have your screw dislocation. If it is in between, then it's a mixed dislocation. That is happening in the curved portion of this transition from screw dislocation to edge dislocation. Okay, এই অবধি কোনো অসুবিধা আছে কারো?
না স্যার ঠিক আছে,
বোঝা যাচ্ছে তো? আচ্ছা, অ্যাকচুয়ালি এগুলো পড়া, সো আই জাস্ট ওয়ান্ট ইউ টু গো থ্রু দেম এগেন. আচ্ছা, now let's come to grain boundary. That's where uh, your uh, uh, your defects. So we had point defects, line defects, and that's where your defects take starts taking the shape. Okay, so as you can see in the left and in the right, there are two different sort of crystals. Okay, where their atoms do not line up. Okay, and essentially form a grain boundary. And as you can see, the grain boundaries in this case, in this example, are formed by a set of dislocations. Okay, so a set of dislocations, because a set of half planes will arrive now. So because of that, a set of dislocations come together and form a grain boundary. So if you look at the figure in the right, the crystals are slightly crystals in the left are slightly the crystal in the left is slightly in off orientation with respect to the crystal in the right, and essentially where they meet, there is a grain boundary. Okay, so what are the purposes of grain boundary? First of all, we have learned about how the plastic deformations happen as the dislocations move. Okay, we'll see that the plastic deformations happen because of the dislocation movement, and as the dislocations move, the plastic deformation happen. And in the last class we discussed about elastic perfectly plastic material, and then we discussed about elastoplastic material with hardening, if you recall, or if you go through that video. So in an elastoplastic material, in the plastic deformation, there is no resistance. Once you go past certain yield stress, the material simply starts having more and more plastic deformation at that same stress, yield stress value. Actually, you don't go past yield stress. As soon as you arrive at yield stress, you start having plastic deformation for infinite amount. So that is elastic perfectly plastic material. The hardening, on the other hand, shows that even to cause plastic deformation, you need to have certain amount of more and more additional stresses. Any amount of additional plastic strain can be created by certain amount of additional. So I should, you can show the drawing also here. Okay, so if this is the strain and stress and this is the strain, so this is the elastic perfectly plastic material, flat line, okay, at yield stress. But if you start having this sort of a behavior, then you to cause any amount of additional plastic strain, although it is not completely plastic strain. So if you want to unload from here, but that still produces an additional amount of plastic strain, right? If you take away the elastic part, okay, so this much is the plastic strain. Okay, so as you have more and more stress, so this is the stress versus total strain diagram. If I take away this quantity, so that would be your plastic strain, and if I plot against it, so this is what elastic perfectly plastic material looks like. kind of rigid and perfectly plastic, because I've taken out the elastic part of the string. And then this curve, that elastoplasticity with hardening, would look something like this. That means even to cause certain amount of plastic deformation, additional amount of plastic deformation, okay, so if it is your delta epsilon p, you need some delta sigma for that. And in the limit, delta sigma by delta epsilon p is called the hardening. So in elastoplasticity with hardening, you need a certain amount of uh, additional stress to cause any amount of additional plastic strain. So that means there is a resistance against the plastic strain also. It's not that as you move from elastic to plastic, there is no resistance. And of course, that additional stress also gives rise to elastic strain. That's what we have been subtracting from here. Now, who provides resistance to plastic deformation? And if I rephrase that sentence, it would have the same meaning if I say that who provides resistance to dislocation movement, because plastic deformations are essentially dislocation movements. Okay, so grain boundaries are one of the sources which provide resistance to dislocation movement in a crystal which is perfect. Okay, where the atoms are oriented, in a given way, the dislocation can shift very easily because it's just shifting from one atom to another. Okay, now when we look at dislocation movement, we'll know what I'm talking about. But when you have certain discontinuity where there are missing atoms, then there are no atoms to transfer the dislocation from one position to another. So you need additional stress to cause that effect. And since we work with on day-to-day life, we work with multigrain materials, therefore most of the materials, ductile materials that we use, provide this hardening effect because there are grain boundaries. Now there could be other sources of resistance as well. There, the substitutional atoms, the interstitial atoms, even more, can be resistance to your dislocation movement. And I work in a field called dynamic strain aging, where the solute atoms at high temperature starts moving. Okay, and as the dislocations move, because you are applying plastic strain, they accumulate again in front of all those dislocations and cause a resistance against dislocation movement. And there are different mechanisms for such resistance, and that gives rise to certain additional rise in stress. Okay, and because of that you have your mm, hardening in the material. So there is this microstructural behavior that is happening, and the result of that is shown in the macroscopic level. Acha. Now let us talk about crystal structures. There is nothing fancy in here. I'm showing only the three basic crystal structure that you are, extremely familiar with. So the BCC crystal structure is not the most closed pack. That means the packing factor is not the highest. However, the most closed packed systems are the FCC and the HCP structures. Okay. Now BCC crystal structure makes up for brittle materials. So in alpha iron, that is one phase of iron, okay, at certain impurity level and at certain temperature. That is the the structure of the that is the thermodynamic structure of iron. Okay, an FCC structure is shown in gamma iron, okay, or austenites. Okay, you must be familiar with the term. HCP is also seen some of the structures, but HCP and FCC are very similar, only different by the fact that uh, so it is only slightly different. Okay, because you see in FCC structure, each plane is this has this hexagonal packing. Okay, uh, and same applies to FCC as well, HCP and FCC as well. Okay, and that hexagonal packing, uh, hexagonally packed plane can be stacked on top of one another in two different ways. Okay, there is a ABC alignment, and there is AB alignment. Okay, so the HCP has that AB alignment. That means there are three sort of stacking is possible. In HCP we only use two of them and repeat them, and in FCC we take three of them. Okay, and mm, and start stacking one after the other. Okay, and that we do not in the vertical direction, unlike the HCP structure, that we do along the body diagonal of the FCC structure. I hope you understand the what is the body diagonal. That is the line joining from 000 to 111 along the direction 111. The FCC structure is ABC. Okay, so you'll have to go back to the details of that to understand what that is. Okay, so by the way, what is BCC? So HCP is hexagonal closed pack. BCC is body centered cubic. So it is cubic with an atom in the at the body. Okay, and that atom is essentially quote unquote touching. You see, atoms do not touch each other. Atoms are not hard spheres. Okay, but if you make an hard sphere model of atoms, that means the equilibrium size of the atom, you consider that to be hard sphere. So essentially in BCC structure, those hard sphere are touching each other. But you know that the atoms are not hard sphere, they're made of electrons and the nuclei, and the electrons are also moving. So electrons move in the probability cloud. So all of those are there. So essentially it is an approximation. Same goes for FCC, but in FCC we have atoms on the faces. Okay, there is no atom at the body center, but atoms on the faces, and they are touching with all the neighboring atoms. Okay, uh, and then there is of course HCP, where hexagonally aligned planes, close packed planes, are stacked one of the other. Okay, so okay, so now the next topic is sleep and the sleep system. Okay. Now, as we discussed earlier, look at the picture in the left. As we discussed earlier, whenever you have an additional atom, okay, for example, in the edge dislocation, you can consider the top half having additional atoms, and the bottom half you can assume just not the top half, the top or the bottom half. You can consider that the around the edge dislocation, the first edge or the first stack of atoms, first line of atoms has one additional atom, and then below that atom is missing. Okay, so the top half is under compressive load and the bottom half is under tensile load. Okay, and that could be the driving force for the um, movement of the atoms. But if you apply a force perpendicular to that dislocation, okay, perpendicular to that or in the direction of the Barger vector. Why am I considering that I'm applying a force in the direction of the Barger vector? It's because that is the one that is counted when we are looking at any given dislocation, edge or screw. It is the component of the force in the direction of the Barger vector that matters, because in the other direction the dislocation is rigid. Okay, so yes, the dislocations have their directionality as well, but again, in a multi-grain structure there are dislocation in different orientation. Okay, and hence even in plasticity you have the isotropy. Okay, so orientation of the grains and the orientations of the dislocations respectively determine the isotropy and anisotropy of the elasticity or plasticity of the material. Dislocation, of course, is associated with the plastic part. And again, since in a multigrain material, the such dislocations could be in any direction. Therefore, there is no directionality in the multigrain material, even in plasticity. So the plasticity is also isotropic. Now, whether it is a screw dislocation or an edge dislocation, it is a component of the force along the direction of the Barger vector that matters. Okay, and um, so this is now look at the picture at the top of the in the right side. So you see the, the movement of a caterpillar. It's like an wave flowing from left side to right side, and by the end of that wave, the dislocation that the caterpillar has moved by a single, unit of distance. Okay, so that is a single footstep, okay, of distance that it has moved. So the wave starts from the rear and goes to the front, and by the time the wave reaches, wave goes past the caterpillar, it has moved by a single quantum of distance. Same applies over here. Now you see we are applying a force. Again, we are showing that the force being applied perpendicular to the dislocation. The force can be in any direction, but it's that component of the force which is parallel to the Barger vector that matters. Hence, as because the other component, which is aligned with the dislocation, okay, so that one actually has no effect. Okay, so as that force is applied, okay, so you see. So you see the dislocation shifts from one plane to another. Okay, so and it keeps on doing, and by the end of the process, the entire crystal structure at the top has moved by a single quanta of distance. Okay, so that single quanta is your Barger vector, and that's why Barger vector is important. Okay, actually, when you write the equation of dislocation velocity, okay, in some advanced courses, if some of you pursue your projects in plasticity, then you will know. If you write the equation of dislocation velocity, there you will see Barger vector showing up, and by virtue of the equivalency, the dislocation velocity is related to your plastic strain rate, and the plastic strain rate also has that Barger vector, okay, in it. Acha. Now, in the bottom picture, we are showing an FCC crystal structure. Okay, and as the FCC crystal structures have that hexagonally closed packed planes. Okay, the one shown in the right, such planes, but they are oriented not along z axis, but they are oriented along the body diagonal. So one such plane is shown on that body with that triangle over there. Such planes are the most close packed planes, and the three directions going from A to F, A to D, and D to F are the most densely packed directions. So on a close packed planes, the densely packed directions. Okay, uh, so the sleep, so the above process that has happened, that results into plasticity. The above picture that we just saw, that is called a sleep. Okay, so that sleep results into plasticity, and that sleep happens not on any arbitrary plane. Okay, even on a FCC crystal, it can only happen. We were discussing, right, that the dislocation cannot very easily cross the grain boundary, because whenever there is a discontinuity, the hard spheres are not touching each other. That is very hard for dislocation to move. Same thing applies over here. uh, the dislocations can only move on this 111 planes, okay, which are essentially your most closely packed planes. That means the atoms are touching one another, and also the dislocations can only move in the direction of directions along which the atoms are touching one another. So there are three such directions. It cannot, move in any other direction. That, for example, in the picture in the right, with spheres being shown with circles, it cannot move along. The dislocation cannot move along, one in a vertical direction. It can move in the horizontal direction, and the two other directions which are making 60 degree with the horizontal. Okay, so there are one close packed plane, and in that there are densely packed directions. Okay, so these directions are so that plane is called the sleep plane, and those directions are called the directions of sleep, and together they form a sleep system. The title of the slide is sleep system. So together they form sleep system. So in a given plane, there are three systems possible, but how many such planes are there? Actually, there are four such planes. Okay, they are called octahedral. planes. Okay, so okay, so I'll make some drawing right now. আচ্ছা, এই অবধি বোঝা গেল কি যেগুলো বললাম?
আচ্ছা যাচ্ছে।
আচ্ছা, তো অক্টাহেড্রন কাকে বলে? সো আমরা যেমন 2D তে ইউনিফর্ম পলিগন ড্র করতে পারি। গন মানে হচ্ছে সাইড, ওকে, মানে মাল্টিপল সাইডস। হেড্রন মিনস surfaces or planes. Okay, so octahedron is a structure which is somewhat like this. Okay, so it has 8 faces. So octahedron is one of the you see there is tetrahedron, there is your cube, then octahedron. There are 5 or 6 regular polyhedron possible in 3D. Okay, in 2D there are infinite number of polygons. Polygons possible, right? Uniform polygon. For example, you can have a isolateral triangle, then a square, and then you can form the uh, mm, mm, isolateral or uniform pentagon, and so on. You can keep on doing this. But 3D, that number is limited. So octahedron is one of them. Okay, and each plane is a triangle. Okay, but you need to understand this plane right there is actually parallel to this plane. Okay, so plane 1 is same as plane 2. Then if you take the plane number 3, which is the one that is facing us, is essentially parallel to the plane that is completely behind, plane number 4. Okay, so essentially there are 4 independent planes and 4 parallel planes that form an octahedron. So so when you take the x, y, and z axis and make identical intercept on each of them, the plane that you get is one of the planes from the top half of the octahedron. Now you see, if you do not look at the negative side of z, so on the positive side of z there are 4 um, quadrants possible, and in each of those quadrants you can have such planes, right? So we can have 4 such octahedral planes on the 4 quadrants. So you have minus y and minus x. Okay, so you can have 4 such octahedral planes, and if you take negative z, there would be just the parallel versions of those planes. So if since they are parallel, they're essentially can be represented with the planes on the top half of the 3D geometry, top half of the octahedron. So essentially there are 4 independent planes, and each of those 4 planes there can be three sleep directions. Okay, since there are 4 planes and on each plane there are 3 sleep directions, 4 sleep planes and 3 sleep directions. So together on each of them there are 3 sleep directions. So together there are 12 sleep systems. That is way too many sleep systems, and that's why FCC structure is so brittle. You cannot find such directions in so many directions in BCC structure, and that's why BCC structure is not doesn't produce such ductile materials. Plastic deformation is not a viable option with BCC structure, whereas with FCC structure it is almost isotropic. So many planes and so many directions of sleep. Okay, so plasticity is always possible. Okay, last topic of the day, and I'll only take up to 11.5. Okay, is the resolved shear stress. Now the actual quantity is resolved shear stress. We put critical for the critical value of that. Okay, so what is that? Here we are showing an example of a single crystal, but that doesn't mean it only applies to a single crystal. With single crystal, we can actually identify the mathematics behind the operation. Okay, it very well applies to multi-grain material. Okay, so imagine an entire cylinder in which the crystals are only oriented in a given direction, no grain boundary. It's a single grain, a single crystal to say. So a grain can be thought of a crystal, right? So you're applying a force in a given direction, and how much of that force applies to a given slip direction? That's we want to find out. Actually, what would be the stress? Now, that stress is actually a shear stress because it is acting on a given plane. Okay, so it is a slip plane and it is in a slip direction. Okay, so whenever a component of stress is acting on a given plane, okay, the component is lying on that given plane, it's a shear component, right? So that shear component, the resolved shear stress, has the expression sigma times cos phi cos lambda. Now cos phi is the angle between the plane uh, and the plane on which the force had been applied, and lambda is the direction between the force and the direction of the uh, slip or slip direction. Now this expression can be confusing to you. Uh, you would think that first of all, this normal and the slip direction, they are normal to one another. Yes, of course they are normal. Okay, but the force F doesn't lie on the same plane. Okay, the force could be lying on a different plane compared to the normal to the plane and the slip direction. That's why the phi and lambda do not add up to 90 degrees. It might at times, but they do not add up. But how do you get this expression? And for that, we'll have to do a little mathematics. Okay, first of all, this force F is acting on this plane right here. So sigma is essentially F by A. But here we are working on a plane whose area is A by cos phi. That is A times sec phi. Okay, so if this area is A prime, it is A by cos phi. How do I know that? A is A prime cos phi. How do I know that? Because if you make phi equals 0, then A and A prime should be same. That means if the normal aligns with this direction, then this A prime area should be same as A. Okay. So this force would be producing a stress. So first of all, so if I were to divide F with A prime, okay, that would be sigma times cos phi, number one. And number two, the component of F that is acting along the slip direction, that is F times cos lambda. The other component is normal to the slip direction. So that doesn't count, as we discussed earlier. So essentially, the resolved shear stress has this expression. Okay. এই পার্টটা কি বোঝা গেল?
Yes, sir.
Okay. এবার, what is a critical resolved shear stress? Now, every time you apply a force on a component, it has resolved shear stress along one or the other slip direction. But does that mean plastic deformation is happening? No. The stress has to reach certain value beyond which the plastic deformation starts. That means the sigma should be equal to sigma y. And once you substitute that, then you have this expression. The expression for the critical resolved shear stress. So actually, if sigma y is your macroscopic property, the microscopic property is your tau CRSS, critically resolved shear stress. So every time this resolved shear stress reaches tau CRSS, you have your sigma reaching sigma y, and essentially plastic deformation is happening. So what do we know from here? Of many things, what would be the most important takeaway for me that whatever force you may want to apply to a component, the plastic deformation is essentially a shear deformation because it has to happen through slip on a slip plane along a slip direction, which is essentially through a slip system. So the plastic deformation can only happen in the form of shear. Okay, and shear deformation has certain property. For example, shear deformation is volume preserving. If you recall the torsional deformation, I'm talking about shear even in elasticity. Okay, so there we made a lot of assumptions before deriving all the equations that we did. Uh, Tau equals 16t by pi dq. So even going into that equation, we made a lot of assumptions that the radius of the cylinder or the shaft doesn't change, the length doesn't change, essentially the volume doesn't change. Okay, of many assumptions, these were quite a few. So wherever you have shear deformation, there is no change in volume. Okay, and because of that, even in plastic deformation is theoretically it is isocoric, volume preserving. Okay, so incompressible deformation, so to say. Okay, so we are more or less done with the microstructural part of that. I mean, we will not. I have any other thing to discuss. So from next class onwards, we will be diving into the main part of the course, which is the theory part.
স্যার এর আগের স্লাইডটাতে একটু তোলা করছে
আগে স্লাইডটা এইটা
হ্যাঁ স্যার এইখানে যে কম্প্রেসিভটা বোঝা গেল কম্প্রেসিভটা কি করে তৈরি হচ্ছে এখানে টেনসাইলটা কি করে তৈরি হচ্ছে টেনসাইল স্ট্রেসটা এই নিচের পার্টটাতে এই লেফট সাইডের যে
টেনসাইলটা কি করে
গোল
তৈরি হচ্ছে,
টেনসাইলটা
কম্প্রেসিভটা বোঝা গেল, টেনসাইলটা বোঝা গেল না। দ্য থিং ইজ, if you look further away from the dislocation, I mean at the top and at the bottom, okay, the crystals are perfect and they are not subjected to either tensile or the compressive load. But there is certain transition that is happening across the edge dislocation. And in that transition zone, no crystal, I mean, no plane, I mean, the immediate planes, just top and the bottom, and maybe a few, few tens or hundreds of planes. Okay, so a few set of planes, you can imagine this plane right there. Okay, so this is where the dislocation is. Imagine the plane just above it and then the plane just above it. There the transition is still happening, so the crystal structure is not perfect, so the atoms are not at their so-called equilibrium distance. Okay, and therefore they are in certain state of stress which happens to be compressive in this case. But if you look at the bottom portion of the field as well, there also the crystal structure has not reached the equilibrium stage until, let's say, this position, until you go past, let's say, 3 or 4 planes. So in the first 1 or 2 planes or 3 planes or 10 planes, let's say, which is not shown here only an exaggerated view is shown with couple of planes. So there the crystal structure is still not in their equilibrium phase, or equilibrium distances. The atoms are not at equilibrium distance. They may be slightly further than the equilibrium distance, and because they are being slightly further than the equilibrium distance, they are under a tensile load.
ওকে
Okay, ওকে, সো এই পার্টগুলো নিশ্চয়ই তোমরা পড়েছো আগে আমি জানি, কিন্তু তবু আমি একবার সাজেস্ট করব এই পোর্শনগুলোতে একটু গো থ্রু করে নিতে। ঠিক আছে, আজকের দিনের অ্যাসাইনমেন্ট এইটুকুই। এই চ্যাপ্টারগুলোতে একটু গো থ্রু করে নিতে, একটু ভালো করে বুঝে পড়তে। ঠিক আছে, আমরা পড়ি পরীক্ষার জন্য পড়ি, কিন্তু ভালো করে দেখা হয় না। একটু বুঝে পড়তে, কোনো কনফিউশন থাকলে পরের দিন জিজ্ঞেস করো। ওকে
Sir,
Okay, sir.
where can we access these recordings?
রেকর্ডিং I'll be sharing.
Okay, sir.
I'll be sharing the links to the recordings. Acha, number 1 and number